Here we have two protons in a box. Their charge is both positive, so they want to repel each other. Let's bring them a little closer, and you can see they do everything they can to repel. Sometimes it's fun to see them almost touch. And I can stop their motion, start them up again. They just don't want to touch each other. Next, I will test symmetry. Start with one in the middle, two off to the sides, along before it goes off center. Doesn't take long. 3-body problem, any little inaccuracy in your simulation will cause chaos. 12 protons, just for fun. You can see them repelling each other right there, right there, right there. There's one. Let's constrain them a little more. Pack them in a whole lot, they have to touch. Black hole. Bang. Nuclear. Now we can stop their motion, let them start up again. If we contain them more and then stop them, we can really let the repel become apparent. They're all stuck on the sides. Here, let's do this. Stop. Open. Here we have 2 protons and 1 electron. Now, the addition of the electron causes these 2 protons to attract because the electron is in the center and they both attract to this electron. And they're closer to the electron than they are to each other. So they're not repelled as much from each other as they are towards the electron, which is spending most of its time in the center. Let's speed it up and see what happens. So they're kind of in an oscillation here. They get close, and when they get close, the electron is spending more time on the outside of the protons, so the protons can repel each other. When they get far, the electron is spending more time in the middle, so they can attract each other. The protons can attract the electron, not each other, but the electrons in the middle. So now they broke the symmetry and they are randomly bouncing around. Let's see what happens. Ooh, they started to attract, but then they were repelled from the closeness of the protons. Let's play with the size of the box to constrain them more. Okay, that proton is really stuck into that electron there. I think they changed. The electron decided to stick to the other proton. Oh yeah, that proton is really getting attracted to that other electron. So the electron's switching partners there. Now we can bring them all to a full stop and restart again. So now, just for fun, let's add 4 particles, 2 protons, 2 electrons. See what happens. Dun, da, da, da. Here we go. Did I do that right? Oh, okay. This is like the cloud of probability. That's one electron, but it's all over the place. Let's slow it down and watch in slow motion. Speed it up again. So definitely one electron is orbiting one proton. This guy is at a farther distance from his proton just because he started farther away. If we stop all the motion and start it back up again, now when we start, they'll both be about this distance from each other. And the only attraction now is to my gravity, and depending on if the electron is on the outside of the proton or the inside, some attraction due to Coulomb's law. Gravity and Coulomb's law are both r squared, 1 over r squared forces, inverse square law. So the farther they are apart, the less attraction there will be, or repulsion. Now, when they're very, very close, the attraction is huge. So I had a theory that gravity was keeping the protons together due to this huge attraction when they're very close together. However, they also get this huge repulsion from charge. So that didn't really work out. They're still floating along. Let's see what happens if we constrain them a little. Add some fade. It's the probability cloud. Okay, let's stop their motion. Start them back up. Let them go faster, slower, faster. They seem to be stuck, but it's really because these electrons are symmetrically around each proton. So net zero charge here doesn't attract a net zero charge here, but gravity, my gravity is bringing them together. That destroys the symmetry in the electrons, so now they're free floating around again. Now this electron is really broke free of that guy's orbit. Let's open the box some more. One problem we have with these simulations is that the distances between the electron and the proton are really huge, and so I'm drawing the proton bigger than it really is in this simulation. If I drew it the correct size, it wouldn't even appear inside of a pixel. It would be so small. Also, I have the electron, the Coulomb's law, cranked down so it's not so attractive or repulsive because, again, the distances would just have to be huge on my monitor and I can't record it all. The reason I incorrectly theorized that gravity was holding protons together was because of this r squared term in the denominator of the force of gravity. When the r goes to 0.01, then the r squared goes to 0.01, and this force gets really great. So when it's 0.000001 down here on a proton scale, the force is immense. And I always heard this statement that gravity doesn't work at small distances, and I thought, well, sure it does. I've always heard it only works at large distances. Well, the thing is, gravity works at both small distances and large distances. But so does Coulomb's force. And in the Coulomb's force, the equation is the same. It's an inverse square law. But you have this K here, which is much, much greater than G. And the charges are greater also. So the force of repulsion or attraction is always overwhelming G at small distances, because at small distances, the electron and the proton can interact repulsively, but at large distances, the atoms electrically neutralize themselves so that the force on a group of atoms, like the the planet's charge is mostly zero at a distance. So, or two hydrogen atoms, the force of repulsion against the two of them, since they're electrically neutral, is zero. So you don't get this force because it cancels out. But gravity never cancels out. There's always a positive force involved. So over the large distances, you get more force of gravity. And at the smaller distances, you still get the gravity, and it's really big, but this is just even bigger.